So my name is Philip Shaw from Shorewave Technology. We've been involved in mine monitoring, particularly seismic mine monitoring, for over 30 years. Started off working with IMCL for the British coal mines, with the few that were left at that time, back in the 80s. We successfully developed a microseismic system that could pick up very tiny seismic energy being released from the strata. The biggest issue with microseismic monitoring is the noise within the environment of mines. Can you imagine a mine has boring systems, it has conveyor belts, it has surface activity, trucks, lagoons, forced air throughout the mine, all generating huge amounts of noise. Noise in the ground, noise in the air, but we're particularly bothered about noise in the ground. Obviously that can be coupled from the air as well. But noise in the ground is horrendous in a mine. In the 80s, a lot of companies emerged throughout the world, mostly South African, Israeli, American and Canadian companies particularly, who said, oh, this is the answer to every mine monitoring prayer. We can detect anything that goes on in mine, locate it, and tell you what it is. Most of those promises were never delivered because of the noise. So I'm really labouring that point. To give an example, microseismic energy release from strata under stress may be 12 to 14 million times smaller than the noise within the mine due to human activity within that area. And it can be within the area. I mean, we're based in Cheshire. We're probably 30, 40 miles to the North Sea. To the Irish Sea. We pick up wave motion with microseismic monitoring. So can you imagine what happens when you put a sensitive accelerometer in a mine? It's going to be swamped with noise. But the good news is there are ways of dealing with that. And if you get that right, you can deliver on the original promises, and there are some remarkable features you can use to give very valuable information. Sorry, just get used to the PC. Page down. Just give me one moment. Ah. Well, that's just... Okay. So, unfortunately, we have to start off with the grim reality of what has been happening around the world. I think I'm not going to labour this too much because you're far more expert in tailing dams and the risks than I am. But that's an example of a couple of incidents that were catastrophic, and we as a company, Shorewave, have to do everything we can to give the mines tools to be able to prevent that, or at least be able to warn about it so that we can prevent loss of life, at the very least. And Shorewave Technology have taken it on ourselves to make sure we do all we possibly can to give better tools. Just to be absolutely clear, Shorewave were not monitoring in Brazil at all at the time of these incidents. Okay, so the numbers there speak for themselves. So, tailing dams. There's experts on the panel who understand how tailing dams are made. One of the biggest issues that we get involved in is obviously the stability of that wall, that dam. And one of the big things that affect that is liquefaction. If you don't know that liquid is getting into those tailings, particularly close to the dam wall particularly, then you could have catastrophic problems. And we were asked by Samarco, post the two incidents that you saw before, we were asked by Samarco to go out, install one of our systems and see if we can detect the movement of liquid in real time at a very accurate level. So what we're doing here is we're looking for movement of liquid from the dam lagoon, from the lagoon of the dam, into the tailing wall of the dam. Also, we're looking for significant movements within the lagoon itself. the technology can detect over considerable distances. So we could actually see what was going on inside the lagoon. Okay, so what's required? You need a 3D model, first of all, of the area to be monitored. That can be the entire dam and lagoon, as an example, which is what's represented there. Unfortunately, that's a static image. If it was on a real system, you can move that lagoon and the dam wall so that you can get different views and different angles. What you were showing there is real data that was picked up live after literally a very short amount of monitoring. A number of days would give you that kind of information. So the system was placed on top of the wall of the dam, and I'll come on to how deep the sensors were in a moment. The blue represents moving liquids that were detected by the microseismic technology, and the red, vertical lines particularly, represent stresses within the wall of that dam at that time. The random red dots you would generally ignore, so long as they don't start to cluster or increase in magnitude or severity or number over time. So you're looking at a random dot once every few hours, you would ignore. But if you get clusters or very significant tightening up or lining of that data, you would want to know what's going on. We mentioned in the introduction, we gave 18 weeks warning for a collapse of a roof. That was at Ashfordby in Leicestershire. The same sort of thing happened there. You could see, we monitored for 4 months or so. We got nothing at all. We were on the verge of pulling out, and we started to get some interesting clustering of these seismic events.
Roof collapse, what caused it?
Pressures that within the mine system that not quite engineered it right. But the problem was they had a competitive system in there. We were a start-up at that stage. We had no experience, no track record, nothing. They had a competitive system in there that cost them around about £1.5 million in 1991. So that was a very expensive system. That didn't detect anything. So when we went back to them and said, we're beginning to see some interesting seismic information that's bothering us, they were like, hold on, we'll go back to our consultants who do know what they're on about. They came back and said, no, there's nothing happening. So what we did, with their permission, we carried on monitoring, and we got Liverpool University involved. And Liverpool helped to look at the data from a geotechnical point of view in terms of rock mechanic data from that information we were giving, because we were giving information of moment tensors, all sorts of rock mechanic information, and we needed someone who was credible who could analyse that data for that mine. At the 18-week prior to the event point, we were able to go back to the mine and say, you have a serious problem, it's going to collapse. And by the way, Liverpool University also agreed with us. They took us seriously. It collapsed exactly on the day we said. Literally on the day we said. They had nobody down there, no lives were lost, thank goodness. Only as a result of the monitoring, I have to say. But they did lose all the equipment. And that phase was closed.
I'll ask you just very quick one. Is this an operating dam receiving tailings or a closed dam?
This was a closed dam at the point we were monitoring, but they were working on the dam because they knew there was problems, which is why they chose us for us to be on there.
Okay.
They subsequently proved that that information there, that you can see on there, was correct. So it wasn't, by the way, this is what's happening, just take our word for it. They actually proved that. Okay. So the object of the exercise is to give a visual representation in real time of what is going on inside the tailing dam and the lagoon if possible. And when I say real time, I mean within 10, 12 seconds of each event, it would be on the screen anywhere in the world for engineers to see and analyse. There is no human intervention required to get that image. This is happening at a machine level on an automatic basis. And the machine is learning, it's stripping out man-made activity all the time. So if new activity starts, the machine recognises it and strips it out, mostly because it locates. So if it locates away from the lagoon and the wall, it knows it's man-made within the mine or the trucks or whatever, so it can take all that out. This is the system that was used. It can be expanded to cover any size of tailing facility of any size. So you could be looking at a 10 square kilometre operation, and this could expand to cover it. Each sensor can pick up to 1 kilometre. We've actually detected up to 5 kilometres. We got involved in gas outbursts for a project in Kazakhstan years ago, and we were able to pick up precursors to gas outbursts, blow-offs, up to 5.5 kilometres if the environment was suitable. So there had to be good transmission of seismic energy between source and receiver, and noise didn't matter, but it had to be a reasonably good medium. Seismic waves do not travel through voids, so you want reasonably compact material between sensor and receiver, source and receiver. So how does it work? I often relate this to, it's got to be able to pick up a pin being dropped on a footpath when the sensor is inside the Royal Albert Hall and there's a full night, last night of the program's going on. That sounds incredible, but that literally is where we are. We're at about 16 million to 1 in terms of, we can pick up events 16 million times smaller than stuff we don't want. Interference, what a better word. So you could be inside the Royal Albert Hall listening to the orchestra in full flow, and a pin could be dropped outside, and we would detect that and be able to locate it and be able to say what it was. And that's where you have to be to get this kind of information that we were seeing there. And that's the tricky bit. So it's relatively unaffected by environmental noise, animals, human activity, mine equipment, and so on. If there's certain activity going on, for instance, while we were monitoring, they decided to drill some boreholes in the front of the dam, mainly to back up what we were doing, actually, to prove what we were doing. Sometimes while they were drilling, we would go blind for a few seconds or a minute or two, but it didn't matter because the seismic energy we were picking up was over long periods of time. So if there's a human activity for a minute or two, even 10, 15 minutes, it doesn't matter, because we just go blind for that period of time and then pick up where we left off. The important thing is we don't false alert on that information. We do know it's not mine activity, so we just switch off there. And this is all automatic. These waveforms are real. So the before waveform literally does contain that seismic event there. So that waveform on the lower trace is literally 1 pixel peak to peak on the top trace. It's that small. So we're extracting all that noise, which looks completely random. Quite a lot of the frequencies overlap, so you can't just filter it with a notch filter or whatever. There's a lot of overlapping of frequency and time domains, but we can strip it out layer by layer and get to the useful information underneath. And if we zoomed in on that and extracted it further, you would have PS wave properties within that, and you'd have all sorts of information that rock mechanic engineers can make a lot of decisions on. Another barrier to microseismic technology was where if you needed to place the sensors right next to where the activity is going to occur, that would require very deep boreholes, it would require intrinsic approvals to get systems within deep mines and so on. We don't need any of that. We mount our sensors on the surface in very shallow holes like that. That's mounted on a spike that's driven into the ground first, and then you bolt the head on from the top. And that's about 18 inches deep or so, towards a metre. Nothing fancy at all. It's got to be on solid ground, compacted, and then positioned like that. And you would cover it up, mostly to get rid of noise within the air, because you don't want planes going over and overactivity to start to transmit onto the top of the metal casing.
When you say solid ground, do you mean
Well,
not in the tailings dam?
Oh, no, in a tailings dam. Yeah. What I meant was you wouldn't dig a hole and then, oh, it's not level, so we'll just put a bit of soil back in and then put it on the top. You would dig a hole into something solid. I call it like the fox bed in Cheshire. We dig down to the fox bed. or you dig down to a clay band, or you dig down to something sensibly solid, not just the loose material on the top. And the spike removes most of the requirements of getting that right, because that spike is quite long. It can be up to 2 or 3 meters depending on the application. Usually they're about a meter length, but that tends to eliminate, you know, being too pedantic over that. But you want it on something solid, because you do need good coupling to the ground. That's critical. Okay? But the point is, you don't need deep boreholes. And that is actually the installation at Samarco in Brazil that we had. Solar powered, unattended for over a year, I think in total. Self-contained, everything comes in that crate, and you can deploy the system very rapidly, except the solar panels. The solar panels didn't come in the crate.
When you whack the spike in and couple it up, you know straight away if it's good enough, do you?
Yes, you'll know. Well, when we install it, or our agent installs it, they will do a walk test along the top of the damn wall. They'll just literally walk back and forwards. And if you can't pick them footsteps up, you've got a problem. Okay. So we can detect up to 1 kilometre. As I say, in some instances we've gone to 5.5 kilometres, but we comfortably limit that to 1 kilometre. It can detect moving liquids, stress of the strata, in other words, acoustic energy as the strata is under stress. But most important, I'll come back to the other one, moving liquids, so you can detect currents within the lagoon. Most of the lagoons are usually solid enough to be dry. That's not always the case. I visited one in Portugal where it literally is a lake. You could go and sail boats on it. But quite a lot of the tailing dams in Brazil that I've personally seen are generally more solid. They've got a crust on them at the very least. So you don't really expect huge amounts of movement of that liquid in there. So we can detect that, but most importantly, you can detect it ingressing into the tailings. So you can see if they're starting to become liquefied. Obviously, I'm a strong advocate of other technology as well. I'm not suggesting for a second that this would be the total solution necessarily. You would also use some existing technology that gives longer term indications of serious slow movements. That technology is invaluable and still has a serious place. But this complements that to tell you what's going on that's not yet producing a movement. So it's kind of a pre-warner of things that might happen later. So it's proven technology. We've been using this technology and deploying in real life now for, well, since 1987 or so. So it's got a very good track record. We've enhanced it, we're constantly developing it, we're constantly moving it forward, and we've gone into security now as well. So we've got a lot of credibility in the security arena. It's actually being used on the country border right now as we speak in Asia. We've been proven to be able to detect trap miners. Because of course, if you can detect microseismic energy, if someone's trapped and they make a noise, then you can pick that up. We have been deployed in real life within the UK to find people underground, and we succeeded. I can talk to you about that privately later if you wish. Some people are saying we're very good at what we do, and that's a quote from one of the military people in the USA. There was a paper written by myself and 2 of the engineers at Samarco. That's available. I'd like you to either give me a business card or send me an email, and I'll gladly forward that on to you. Thank you very much for listening.
Oh my goodness, well done. Thanks very much for that, that was great. I think what we'll do is we'll just get the 5-10 minutes or whatever from each of you two, if you don't mind, and then we'll have questions at the end. I think that's probably an easier way of timing it, if that's all right. So, you want to start?
Yes.
That would be great.
Philip, I think most people here will agree with me. This is very interesting technology. I mean, anything I think that could potentially save lives, I think is something that we need to set up and take notice of. So thank you for your presentation. From a kind of mine-waste disposal kind of practitioner, and I'm not a geotechnical engineer, I think if you kind of look at tailings liquefaction, we mustn't try and oversimplify it. Oversimplify the whole liquefaction or tailings liquefaction, because it is quite a complex phenomenon. Now, my understanding of it is that you generally end up with tailings that can have liquefaction potential. Generally, when you look at really fine, very loose tailings, and it usually has to be under the water table, under the phreatic surface of the tailings dam, before it's susceptible, or before it may be susceptible to liquefaction, which is effectively a sudden loss of strength. I think if we kind of look at generally at tailings facility stability, I think a large part of that is all about water management. If you manage the water and you manage your deposition, and you allow the tailings enough time to consolidate, in many instances, you don't end up in trouble. I think the interesting thing for me about, and I think a bit of a shock for many people, the Bernardino, the second failure in Brazil, was how suddenly it happened, and the fact also that it was a closed facility. Because I think there are potentially quite a number of closed facilities out there that are effectively, I mean, I don't want to sound or be sensationalist, but I mean, some people have compared it to a ticking time bomb. So I think the type of technology and the system that we've used here for the developed for the coal mines, and also used for the monitoring scenario, looks very promising. Generally speaking, if you kind of look at, I would say, conventional tailings facility monitoring, we look at the construction of engineering works for the facility. This is now for active facilities and active mines. We generally assess the piezometer data that the clients or the mining operators kind of generally take on a weekly or a monthly basis. We also look at drain flows, tailings deposition, which areas of the facility they are busy depositing tailings on. Also monitor wall movements. There's a couple of systems that can be used for that. Inclinometers is one. Servo monuments with conventional servo with the total station is another. And then we also look at geochemical assessments, as well as the tailings parameters itself, particle size distribution, and the other kind of general geochemical parameters of the materials. I think on most tailings facilities we're involved with the monitoring, we generally do quarterly facility reviews for our clients. More often, if we kind of pick up that there are potentially issues with the facility, then we would go down to monthly monitoring. And then generally, on an annual basis, we do a TMF audit, which is also legal requirements in quite a number of European countries. If you kind of look at kind of improvements on tailings facility monitoring, I think to a large extent it is to develop a monitoring system for the client that actually gives them, allow them to, and the consultant to monitor the facility on a reasonably regular basis, and especially to pick up if there's anything that's unexpected or that doesn't follow trends that's been established previously for the facility. We kind of had a discussion with some specialists from geotechnical observations here in the UK. They've also been involved in some monitoring for the Crossrail project. And one of the kind of new, I would say, technological developments that they started using in many of their projects is a shape array, which is basically an array of rigid segments separated by joints that can move in any direction, but they generally do not twist. And by monitoring that, it gives you, I think, slightly more accurate readings than you would get with a conventional inclinometer, and that can also give you a good indication of ground or structural deformation. I mean, in Crossrail we used it basically to look at deformation of tunnels, but you can also install it vertically or horizontally on the tailings facility or other civil engineering structures to actually monitor it. I think two other developments is to actually install total stations to basically function as a continuous monitoring system based on a number of fixed points or prisms to actually monitor either movement of buildings or your monitoring points on a TMF embankment or tailings storage facility embankment or a water retaining structure or any other civil structure for that matter, as well as basically integrating that system as well as automated monitoring system for basically looking at piezometer readings as well as all the other readings from your server system or your monitoring beacons, and to actually link that to a system that can upload that via the internet and the 3G or 4G modem to a database that's basically cloud-based that you can access as consultant or client or design engineer from anywhere in the world. And I think that is definitely something that we'll need to look at in the years, over the next couple of years. I think the biggest advantage of that is it's real-time monitoring. You don't wait for a month, for example, before you get some survey data from a client or a tailings operator before you can analyze it and actually realize or pick up that there might potentially be a problem. So I think I'm quite excited about it. I think there's definitely a great opportunity for us on developing systems like that and implementing. I think the main thing though is you actually need to show to the client the benefits, and I think one of the biggest or best ways to motivate it to them is just from a risk management perspective, because it just makes it easier for them to manage their risk. You can deal with problems sooner, and I think also from an insurance perspective, as clients, it makes a lot of sense for them, also for us as mine waste disposal consultants. Thank you.
Brett, would you like to give us your 5 minutes or 2 minutes or whatever?
I'll try to get to 5 minutes. This was a little bit of a short notice for me, but yeah, I think it's kind of an interesting time for us with recent failures and the way that we're trying to adapt technology into the monitoring for tailings dams, and I think each technology has its kind of own purpose, and it's not suitable for every facility. And whether we're starting from scratch from a new facility, I think you need to have that robust design and the complete quality control and quality assurance for construction, identifying good materials, and identifying the appropriate monitoring to implement for your location. And I know in my experience, when you have maybe a bit more fancy technology, that becomes a valuable target for theft, and a lot of facilities are a bit more remote, and yes, we can power them by solar panels, but a lot of times it becomes a higher target, so we have to be a bit more creative in how we use these new technologies and whether it's appropriate. And yeah, I guess maybe the way that we approach it is looking at whether it's necessary. We look at the hazard of the facility, type of hazard rating, and go from there. Just looking at some of my past experience, I could see this system would be useful, maybe not necessarily intended for, say, liquefaction, but identifying, we're seeing increased seepage through the dam. We're not able to locate what the source is. and a lot of times it's just deposit tailings, push the pond away. But I can see something like this system being a useful tool, whether it's kept in place, permanently, or just brought in to do a short-term kind of test to identify where that, the increased flow is coming from through the dam, to allow you to make, I guess, educated decisions later on. Yeah. I think for a lot of facilities, we kind of stick to the tried and true, vibrating water piezometers, have a few standpipes just to confirm and allow those to also be sources for collecting water samples for testing, just your standard settlement monument. But we're definitely expanding, looking at the technologies, and we've had a lot more discussions with companies that provide that real-time monitoring solution, and it's being able to use that technology, but not just having the client, or at least the client knowing what to do with that technology and that information, and having the client engage you to be a bit more, I guess, involved on a routine basis, not just on an annual basis or a quarterly basis when you're doing audits, but on a regular basis, inspecting the data. Sorry, lost train of thought here. I think, having that real-time solution, but adapting, say, trigger levels or response levels so that it's not just data that has to be then manipulated or to be reviewed, that it can notify people and correct, so that people can take corrective measures or actions. I think, sorry, a little all over the place here, but I think it's having that technology, but not just becoming data, that it becomes useful data, that there's a system that can take that data and give you further advice as to what to do, whether it's okay, you have in terms of this system, if we've identified flow or water moving, is this acceptable, or if it becomes critical, what's the next step, or at least notify, so that it's not, okay, we have data from the last month, now someone needs to look at it, it needs to be on that real-time solution.
Good, thank you very much. So have we got any questions from the floor for either of any of these gentlemen? Yes, good.
Thinking about the likelihood of tailings to liquefy, there's possibly a glycol. How fine is fine when it comes to the risk of tailings when you feed it into the facility?
It depends. There is a screening test that you can do. So it's basically, it has to do with the PSD, but sometimes also not 100% sure whether the mineralogy of the tailings has to do with it. But I think it's the particle size distribution as well as the density of the place material. So there is a screening test that you can do, and generally what we do is we do the screening test first to identify whether the tailings might be susceptible to liquefaction. And if it actually doesn't, or basically if the answer to that question is yes, then we generally do some drilling and take samples, and then do some geotechnical laboratory test work to look at that.
Does the crystal habit of the tailings mineral have much of an influence? Say, micro-rich or some cubic system as you feed into the different side, particle shapes matter.
To tell you the truth, I'm not sure. There's probably somebody who's done a PhD on that.
Any other questions?
The liquefaction events, are they always actually triggered by a small tremor? Or can they just be like, it gets to a critical point and it does it itself?
I think there generally has to be something to trigger it.
Yeah.
I think static liquefaction, basically exactly what triggers it, I think is sometimes very difficult to determine. But I think the easiest kind of, or the easiest or most common event I would say to actually trigger liquefaction is usually seismic events. So if you basically have an earth tremor or an earthquake, that tends to cause liquefaction.
But yeah, it's
Provided the material is susceptible to liquefaction.
It's definitely not just a seismic event or a terminal. Various triggers from the static liquefaction, and I think, in terms of testing, we do a lot of CPQ work, especially for upstream or central line tailings dam raises, and looking at that susceptibility to liquefaction from those correlations results here from the CPT, and I think there's probably a lot of test work that you could do to identify what those triggers could be. A lot of times you just end up assuming that it will or can liquefy as part of your stability analysis, and you're not looking at specific triggers.
You mentioned the upstream design there. Can you, I know it's a bit of a crazy question, but how much more risky is an upstream design compared to a downstream, on average?
I think it depends on how well they design.
So maybe a question for the conference next week.
I'm afraid I'm on site next week. I work for the insurance world, and I've got about 4 trips really triggered by people's nervousness. These bigger events, but I'm only going to tiddly places.
I think it's the case, it depends on facility by facility and the environment that it's been constructed in, how it's been designed, as well as the tailings material actually placed and how it's placed. I mean, in South America, basically one of the things that they've done there for a number of years is actually to cyclone the tailings to actually get the pore structure out. They place it with very flat outer slopes, and then they also compact the material when they do their raises. So if you're in a seismic active area, you actually have to design it. And I think it's also important to remember that it's not just for the operating phase, but that facility is potentially going to be there, or definitely going to be there for hundreds of years. And it actually has to remain safe during that entire period of time. So design for closure is actually much more, or much trickier, I think, than many people realise.
John, you have a question?
Yeah, so Philip, I was just wondering how you managed to locate these events or these micro events. Is it just simply by triangulation from different sensors, or?
That monitoring there was from 2 sensors, so we couldn't triangulate. So we were locating by PNS wave, time difference and overhead techniques. But we do recommend a minimum of 3 sensors going forward. That was one of the things that Smartco didn't like about that monitoring exercise. But it was the only thing they didn't like, actually. They loved everything we did there, and they did some remedial action based on the information we gave them, and that dam is still there. And one of the things they didn't like was the uncertainty of location instantly. We only guaranteed the location after a period of time when we'd had several events in the same place. If we could triangulate, then it would have been less events.
You said that you had your sensors in place for several months
Yes.
before, and you were just about to disband them and take them away when you actually started picking this up.
That was the mine.
Oh, that was on the mine, right, okay.
Yeah.
But I mean,
This was picked up instantly. That's Smartco.
okay. So, I mean, I guess the question is, how do you, under what circumstances do you install it? I mean, do people, we think we might have a problem, can you come and check? And are you going to be there for 6 months?
Yeah, very, very good question. In an ideal world, you'd get a baseline reading. If this was a coal mine, and you were monitoring for, say it was an abandoned coal mine, you're looking for ground stability in that area. You would ideally go in there and establish a baseline when everything was fine. And you'd be looking for a significant change on that baseline. And a significant change would be 100 times, more seismic or something. You would not be looking at very small percentages of change at all. When these events are happening, in the mine events and other things we've monitored, the significant difference between a stable situation and something going wrong is enormous. There's not a fine margin with this kind of technology. So you ideally get a baseline, but you can do what was suggested by the panel. You can actually do almost a day's monitoring. Not literally, you'd be in there for at least a week or two. But you can have a portable system that literally would travel around and take spot checks. That would be one way of doing it. I mean, it's not ideal because we all know you insure a car. If you decide you can pick the days of the year you're insured and therefore reduce your premium by that amount, you're going to have the crash on the day you're not insured. It's bound to happen. So it's not an ideal situation, but it is a possibility where you could go and have a look at mines. Because the data is literally instantaneous, within 2-3 days you would have an image similar to that. Hopefully it would be flat. And we have gone to sites where there's nothing to monitor. But in an ideal world you'd monitor permanently, particularly if there's a problem.
Is that something that you could set up, that it would be there as a permanent monitoring?
We have had semi-permanent installations that have gone for many years. And they've only come out because it was proven there was nothing.
Brett's point about where it is quite important, because a lot of places it would walk very quickly.
Frankly, we've never had that. We do a lot of civil engineering monitoring, like network rail and so on. We're at Waterloo Station right now. On a civil engineering level, nothing to do with what we just talked about. We've only ever had one of the civil engineering units stolen. We've never had a mine monitoring system or tailing damage system stolen. Can I just pick up something that you said? I totally agree quality control is far more important than monitoring after the event. If the quality control of knowing what tailings are put down is absolute, then the likelihood is you should not end up needing this kind of care. Forgive me, but that's what you said.
That's a very valid point.
Yeah.
I have to agree with you.
The quality control is right. I mean, this kind of is almost an after event. You potentially got a problem. Do you want to go and have a look and see whether there really is something to monitor that might?
The trouble is that, like the dam that failed in January, they've just had it monitored. They just had an inspection that didn't pick anything up. I mean, one assumes that it wasn't giving any precursor
We'll never
clues. But as you say, the trouble with the tick box exercise, where a mine site has a tailings dam and they know that it's got to be audited every year, and somebody's going to do a quarterly check, but it's only if something is happening at that point in time that is the issue. And also, as you were saying, there's thousands of apparently closed tailings that potentially have the same risks. So, what do you think the answer is? That, like, every mine has to have, every dam, regardless of whether it's closed, has to have an annual check, and using some sort of technology like this, or
you could probably have a look at the management. You could probably start by putting a risk factor on the mine in terms of, do you absolutely know the right tailings are put in the right place? Has it been professionally monitored and done? So you could probably, and there's probably a very tiny number that are really at risk. In the real world, forgive me for saying that, they'll all collapse tomorrow. There's probably a very small risk. It's just identifying the one that's going to be the next one, isn't it?
Philip, I think it's usually a combination of factors. I think if you start with a proper geotechnical investigation of the site, and you have a well-designed facility and it's actually constructed as it was designed, that's a good start. And then if you, in a perfect world, if you then have a responsible team that actually manage the operations on that facility, then you're almost there. I mean, that goes a long way to actually get a reasonably safe facility.
Isn't it misoperation though, or operation
where you're putting too much in, where the tailings dam is under pressure to take more material for whatever reason. There's been heavy storms, so that levels in the dam are increasing. So is it not more of an operation issue than a design issue in your experience?
Well, I think it's generally a combination of the things, but what you've just mentioned, that point, is actually really important. Because I read a paper recently, and effectively what they concluded was that if you kind of actually look at mining operations, there are, if you look at the number of large mines in the world during the past 30 years, the ore grades have gone down, whether you mine copper or gold or any other commodity. And the facilities have increased in size. And I think that basically what they concluded was that they think that the biggest risk lies with the medium to smaller mines that's actually really pushing the limits on the facilities and pushing them further than those facilities originally were designed for. Yeah. And that's where potentially where the problems start.
I would have thought another potential threat would be when a company gets taken over by another company, and you lose, you know, they might change consultants, or the geotechnical or the tailings dams engineer leaves or whatever, so nobody knows what happened in the past, and then when they try to add to that tailings dam, that's possibly where issues arise.
I think there is generally a bit of a risk. I mean, even if you look at just staff turnover at mines, I mean, often you actually have somebody with years and years of experience, and they basically don't do successive planning, and your tailings guru that you had at the mine retires, or something else happens, leaves for another mine, and you actually lose some of that knowledge. And that is actually something that is really critical. I mean, also to ideally have a similar or the same consultant for a number of years that actually knows the history of the facility. Having said that, to actually have third-party review is unbelievably important, and I think makes a huge difference. And I think if there's a consulting engineer that has a problem with somebody else reviewing his or her work, then that's not the type of engineer you actually want to have managing your facility.
That was one question I had actually, because there's not a consultant as a co-author of paper. It's the mine and yourselves. Was the results of your work independently evaluated by were consultants involved, like these guys? Were they involved?
There was a consultant group involved that carried out the remedial work to prevent it, to correct that problem that was on the 3D model.
Right.
They took our data and corrected it. We had no involvement in that.
No.
Just a more typical question. The sensors you had buried, do you need a power supply for them?
They're cabled. They're not wireless sensors. They're cabled back to the unit.
But they need to be powered up. So you
Yes, from solar panels. Yeah.
And the data is taken from them to this box tricks.
Yes.
And that holds the data and analyzes it, or is that then taken to a server somewhere?
No, it's all analysed locally at the unit that's cabled, the sensor's cabled to, and then the image is sent to anywhere in the world to be monitored by consultants or experts, or just the mine office at the facility.
But you would need a power supply at the dam of some.
Solar, yes, usually solar.
Solar power.
Yeah, I mean, we monitored a slate mine in North Wales. Getting solar power to work in North Wales is as bad as it gets. Particularly in winter. Well, partly because the mine was so deep, actually. The angle to the sun was terrible in winter because it was mostly below the crest of the... but we worked perfectly on solar power.
You're using 3D accelerometer?
Yes, they're traction.
Have you ever come across using fibre optic cable for sensing?
Yes, there are competitive systems for security. A typical security scenario down the border, you would run a fibre optic cable. If you get to within 5 metres of that cable, it disturbs the cable enough for it to be detected. They're our competitor. We detect up to 1 kilometre. They can detect up to very narrow corridors.
Okay, but...
And by the same definition, if a fibre optic cable is placed within a tailing feature and that feature starts moving, or has any vibrations in it, that fibre optic cable will pick it up.
There was a paper I was reading in Australia where they laid fibre optic cable along the surface of the tailings dam, and it was just relying on ambient noise, and the change in speed of sound it was picking up on ambient noise could then detect the breakdown of the internal structure of that, and then predict where it was going to fail. So not through seismic activity, but through the fact that the speed of sound was changing for a certain part of the dam, and just by picking up ambient noise,
Yes.
any ambient noise.
And may I throw in a few others? There's all sorts of other systems that can allegedly monitor the tailing features facilities. For instance, measuring the resistance of the earth, you can determine the water saturation within, between the sensors. Yeah, there's a lot of those. I've got to be honest, a lot of the people who deploy them, for instance, we've had discussions with United Utilities, because they've tried that to find leaks from dams, serious leaks from dams, because most of the reservoirs leak to some degree, but serious leakage, and they're not happy at all with that kind of technology, and they're potentially going to look at ours. But the biggest problem of our technology for United Utilities is that they expect it to be, a couple of £1,000, and it isn't.
Well,
But
how much is
that's
it?
Pardon?
How much is it?
For a typical mine monitoring feature facility, you'd be looking at about 100,000, 150 maybe, depending on the size.
And if you stuck it in and you did your monitoring and you were happy with it for a while, if you sort of like stopped the monitoring but left the hardware around and then, turned it on again later, you could cut the cost a little, or is it monitoring on the hardware?
It's the hardware. There's no monitoring cost as such, unless you want to pay consultants to check the data. But you shouldn't need to be fair, because you should visually be able to understand that picture and know whether that's what it was designed to do, or whether this is something new. Because it could be designed to have water transfer upgrades. Well, that's not. But you need to, it should be in the right place. We did a monitoring exercise in Australia for Eaglesfield mine, and they had an aquifer one side of a very narrow seam, which they knew about, but they got some disturbing data from other sources that they thought the mine was going to be on the other side that they wanted to move into. They quickly set this up. We were only there a weekend actually. We were live by Friday evening and we were taken out Monday morning. They found another aquifer and they mapped it and boreholed it and so on and proved it was absolutely spot on for what we said. We picked it up in, like I say, 3 days, 2-3 days. So it can be used very quickly just to establish either a good situation, it's doing what we designed it to do, or a bad situation.
But also, I think, as you said before, to actually establish the baseline data, so you actually have something to compare at the start of the project with.
Yes, that can be important.
Right, guys, it's 7 o'clock, so I think if we continue any further questions that people might have over some snacks and drinks and things, and take it from there. But thank you very much, guys. That's really good.